Okay, so we're starting chapter 4, which is all about exponential functions and logarithms. It's only 5 sections, not anything too crazy that you're going to see here in chapter 4. Sometimes the students have trouble solving the equations, so we're going to try to make time for that, especially to kind of slow down a little bit on the equations. But we're going to start out talking about what are exponential functions, what do their graphs look like, and then we're going to contrast that with logarithmic functions when we get into 4.2, which we will a little bit later today. Logarithmic functions are going to be inverses for exponential functions, so you'll see how one of them relates to the other, and you kind of work back and forth. So for now, we'll talk about exponential functions. We're going to evaluate them and graph them today, mostly. So the exponential function f with base b is defined by f of x equals b to the x, or y equals b to the x. Now, the difference here, you might be thinking, like, okay, how is this different than what we've talked about so far? Well, the big difference is that b is a positive constant other than 1, so b is greater than 0, does not equal 1, and x is any real number. So what you're going to be seeing here is instead of having a variable taken to a power like you've seen before, and in this chapter we're going to be seeing a lot of a number taken to a power that is a variable. So you're going to have the exponent you're going to have a variable in your exponent in most cases. Okay. All right, so let's see. Talked about the definition here. We can go ahead and just evaluate so you can kind of see how this works, seeing this in an application problem. We'll just evaluate this one, and then we'll talk about how to graph these exponential functions. Number 1, the rabbit population in a forest area grows at the rate of 5% monthly. If there are 150 rabbits in September, find how many rabbits, rounded to the nearest whole number, should be expected by next September. Now, you are given this function, y equals 150 times 2.7 to the 0.05t. Now, remember that t is just, well, actually, you weren't explicitly told what t is here. But if the rabbit population is growing 5% monthly, then we can assume that t is the number of months that are occurring in the problem. So even though we weren't explicitly told how many months we were looking at here, we're talking about what's happening from September to the next September. So from September to September, we're talking about 12 months. So that's what we're going to be evaluating. Oh, sorry, I missed a question in the chat. I don't know how this keeps happening. Is my volume not on? All right, are we skipping 3.6 to here? Yeah, we're skipping 3.6 and 3.7. So we kind of talked about that last week. Okay. All right, so let's see. Find how many rabbits rounded to the nearest whole number should be expected by the next September. So we're going to take our function, and I want to remind you here, because we're going to be using our calculators quite a bit. These are the types of functions you're going to need your calculator to evaluate. What the value that's being taken to the exponent is not 150 times 2.7. We're going to have to use order of operations here. You're taking 150 and multiplying it by 2.7 to this exponent. The exponent has to get applied first. Just making sure I have everything in the chat. Okay. So we're going to go ahead and apply or evaluate what's happening in this exponent first, and then we'll talk about how to actually find the value of y after 12 months. So if we're talking about September to September, we're going to let t equal 12. And remember that that's in months. And then y is just the number of rabbits that are in that population. And you're expecting, because the rabbit population is growing, which makes sense, that the number that you get is going to be larger than the initial number you were given, which is 150. And we're going to be writing these types of functions when we get into 4.5 and we talk about growth and decay. So let's go ahead and evaluate, and we'll let y equals 150 times 2.7 to the 0.05 times 12. I had some questions in the last chapter from one of you specifically asking about whether you should round your work before you get to the final answer. Don't. I want you to enter all of this at one time. So when you put this in your calculator, you should be entering 150 times. Now, you don't have to put the parentheses around the 2.7. You can just write the 2.7 to the, and then if your calculator's newer, you'll get an exponent box. If your calculator's older, you're just going to see the caret and the parentheses. That's fine. Just multiply inside your exponent. 0.05 times 12. Well, 12. And then this will give you the rabbit population after 12 months, which you're hoping is more than 150. Of course it is. Now, don't put down 272.213. You're being asked to round to the nearest whole number. So in this case, we'll round down to 272. The reason I wanted to talk about intermediate rounding, and let's see if we do end up getting something different if we were to round early. It sometimes happens, but not always. Let's say you first decided, and you wouldn't get an error here with the exponent, but let's say you wanted to take 12 times 0.05, fine, and you would get 0.6. And then if you decided that you were going to take 2.7 to that answer, then you would get this value. Now, if you were to round that at like 1.8, let's say you did that and you were like, okay, well, let's take 150 times 1.8. Don't do this, by the way. I'm telling you what not to do. Your answer would actually come out as 270. This is why we don't want to use intermediate rounding. That means we don't want to round off our values before we get to the final answer. So don't do this. What I would ask you to do if you were doing this in pieces would be, okay, fine, multiply your exponent, take 2.7 to that exponent, and then multiply by 150. If you just hit multiply, it's going to pull up your last answer, and that will get you that 272.213411. All right, so the moral of the story is don't round until you're all the way to the end. Put everything in at one time, and if you're not sure if you're entering everything into your calculator correctly and you want to do it in pieces, that's fine. Just hold on to as many decimal places as you can carry around. Any questions about number one? Michael got 1,890. Let's see if I can duplicate what he got. Let's see. If I did this, what would I get? No, let me get that. Something is amiss, Michael. I wonder what I put the exact equation, but I'm on an older calculator. If you're on an older calculator, I wish I still had my old one because I know a lot of you still have old ones and it's kind of nice to be able to see how it works on the old one. Let me see what you could have possibly done to get that answer. Let's see, 2.7. You use the caret symbol and then you got a parenthesis. I wonder, did you close off your parenthesis too early? Could that have happened? 0.05 and then maybe times 12. Could you have done that? Oh, is that what you got? 1891.64. Yes. Okay. Yes. So the 12 that you entered was not part of your exponent. So if you're using an old calculator, and you ended up putting in 150 times 2.7 and then caret, and then it opens up your parenthesis. And then you say 0.05. Don't close your parenthesis. Multiply by 12 and then close the parenthesis. I'm guessing that was the issue, Michael. Did anyone else get something different you would like me to investigate? See, I like stuff like that because at least I feel like now it's better that we're having this synchronous class, because if you were just watching recordings of me teaching, you wouldn't be able to be like, wait a second, I'm putting stuff into my calculator incorrectly and I don't know what the problem is. See, we're live together. It helps, right? We hope. Let's talk about how to graph these functions. Okay, we set up a table of coordinates, then plot the points connecting them with a smooth continuous curve. Now, I'm guessing right now most of you don't know what you expect this graph to look like, but once you start to graph these, you're going to notice that they all look pretty similar. Some of them are going to ascend more quickly, or some of them are going to descend instead of ascend, but they're all going to be doing similar types of things. So you're going to see what this function looks like. First, let's make a table of values the same way that we would when we're graphing any type of function. We're going to pick some values for x, and then we're going to choose some values. I don't know, the same ones we always choose. Probably -2, -1, 0, 1, 2. You can do that. And then if you feel like you need more, you can always include more. Kind of depending on your value, you might be able to fit more in. 2 is a smaller base, so you can do a little bit more with 2. Okay, now we have to know how to evaluate exponential expressions. So when we are finding f of -2, we'll have 2 to the -2nd power. Now, of course, you can put this into your calculator as 2 to the -2, and you'll get 1/4. If you don't want to put it into your calculator, remember that 2 to the -2 can be rewritten as 1/2 to the 2nd. Sometimes if we just at least know how to do this stuff without our calculators, it at least gives us another way to verify if our calculator answer makes sense. So when your exponent's negative, remember you can move that expression to the other part of the fraction and make it positive. All right, so we have a point. Might as well fill out the rest of my table. At -2, +1/4. And then we'll do the same thing for the other x values. F of -1, 2 to the -1st power is 1/2 to the +1st, which is 1/2. Some of you are used to seeing that negative first exponent as being like a reciprocal, so you can always think about it that way instead. And that's another point on the graph. F of 0 is a kind of an anchoring key point on these graphs. F of 0, in this case, is 2 to the 0. Any real number to the 0 power is 1. Don't forget that. You're going to use this a lot. A real number to the 0 power is 1. Your calculator will give you that too. F of 1 is 2 to the 1st. Any real number to the 1st power is just itself. So you'll also have a point at 1, 2. And then for f of 2, 2 squared is 4. So we'll have a point at 2, 4. My suggestion to you would be plot these points, and then when you look at your graph, you'll be able to tell if you need additional points to be able to determine the shape of the graph. This one's not being shifted any direction, so we should be good here. You have a point at -2, 1/4, and just do your best with these fractions. 1/4 just comes up off the axis a little bit. -1/2. 0, 1, there's that anchoring point I was talking about. 1, 2, and 2, 4. Now notice if we were to keep going to the right, if we looked at something like x equals 3, well then we would have 3 and then 2 to the 3rd, which is 8. We actually don't have 8 on our axes. You can put it up there if you want and get a good idea of what would be happening at 3. You don't have to because it's not really here. I'll just pop it on there just to give you a good idea. So what's going to happen here is as you keep increasing the exponent by one integer after the next, or really as you keep increasing it at all, your graph is going to start to increase more rapidly as x becomes more positive. So y is also going to approach infinity. But you'll also see that if you were to do the opposite and you were to choose values of x that were smaller, in that case, you're using the reciprocal of all those values. Now notice that your denominator would keep getting larger, but the numerator would continue to be 1. So you would have 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. And even though these fractions continually lead you to smaller and smaller and smaller values for y, you're never actually going to hit 0. You're going to approach 0, 1/64, 1/128, yada, 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 and you're never actually going to reach y = 0. So officially, you have an asymptote on your graph, this horizontal asymptote. You don't have to draw it for the exponential functions. I just want you to know that it's there. And we'll connect these points with a nice smooth curve and just make sure that you don't cross over the x-axis. And that is what the graph of an exponential function looks like. Any questions on that? Okay. So back in 2.5, we talked about a lot of different transformations for functions. We talked about the simplest ones, which were adding a value or subtracting a value from the function. So the function would go up or down. We talked about moving the function left or right, and that would happen inside whatever is happening in that function. But we also talked about reflecting your function across maybe the x-axis or the y-axis, or stretching it. You're not going to see too many horizontal stretches and shrinks, but you're going to see more vertical stretches and shrinks here. So as we work through these, even though most of the time you're going to be using a table of values, you can kind of eyeball this and see like, does this line up with what I think the graph is supposed to do based on what I know about transformations? So let's do number 3, which is f of x = 1/3 to the x. You know, it's a little trickier because you're dealing with a fraction. Now, that whole quantity 1/3 is being taken to the exponent x. And we can use the same values for simplicity. Again, we're not shifting anywhere left or right, so these values make sense for us. It's especially important here to choose values that are both negative and positive. Note that had we not chosen negative values up here for x, you wouldn't have been able to see this behavior of the graph approaching the x-axis. You wouldn't really know what was happening. You might just say, oh, it's going up. And then, I don't know, maybe you would have done something crazy like make it look more cubic. So it's really important to make sure that we include different types of values here so we can get a good picture of what's happening with the graph. All right, so let's go ahead and evaluate f of -2. So we have 1/3 to the -2nd power. And remember your exponent rules. If you want to make the exponent positive, you can switch the numerator and denominator, because essentially this is 1/1/3 squared, and 3 squared is 9. And that gives you a point on your graph at -2, 9. f of -1, similar idea. 1/3 to the -1st power is just 1/1/3, which is 3 to the 1st. I guess we can just leave it as 3. So this is -1, 3. And then we'll find f of 0. Now, again, any real number to the 0 power is 1. So it doesn't matter if it's a fraction or if it's an integer. As long as it's a real number, take it to the 0 power, you get 1. And once we start looking at positive values for x, this gets even more straightforward. 1/3 to the first power is 1/3. And 1/3 squared, remember, is 1/3 times 1/3. If you don't want to write it that way, you can technically just take that exponent and apply it to both the numerator and the denominator if you prefer to see it that way. And you get 1/9. But again, you're seeing the same behavior that you saw with the original or the first function that we did, which is that these numbers that you originally saw in the denominator are popping out now in the numerator, and vice versa. You saw these values by themselves, and then as you work your way into these positive values for x, you're seeing them in the denominator. So let's go ahead and plot these points. -2, 9. Oh, haha. I guess we don't have 9. We can fix it. We can make it be on here. 7, 8, 9. -1, 3. 0, 1. 1, 1/3, and do the best you can with these really small values. 2, 1/9. So now you're seeing that as once the numbers in your base start to get bigger, even just using numbers like 3 versus 2, all of a sudden we have this behavior where the graph is increasing more rapidly, this time as you head towards values of x that are approaching infinity, or I'm sorry, negative infinity. So let's go ahead and connect these with a nice smooth curve. Try to make it look like you're approaching the x-axis. I know it's kind of hard to do. As long as you don't show it like swinging back up again, I'm not too crazy about how far away you are from the axis. Do the best you can. I know it's very close. All right. Does anyone have a question about this graph? Okay. What do you guys think of comparing these two graphs? Why is it the case that number 2, as x gets larger, f of x gets larger, but for number 3, as x gets larger, f of x gets smaller? Why is that? Is it because of the fraction? Yes, but not necessarily because it is a fraction. What's specific about the fraction itself? Like, I mean, what if I had 4/3 to the x? Would I still be expecting to see something like this? It definitely has to do with the fraction, but yes, because it's less than 1, Elizabeth says in the chat. Sorry, I should have specified. The deal is, for number 2, the base was greater than 1. For number 3, the base was less than 1. So just because it's a fraction in and of itself means nothing. It's because it's a fraction that's less than 1. And as soon as we get this fraction that's less than 1 as the base, you're going to see this behavior where now we're not increasing as x goes, becomes more positive, but the function will be decreasing for larger values of x. That's the big difference. So it's really important to understand the characteristics of these graphs so that you can kind of check yourself and say, wait a second, like this shouldn't be doing whatever behavior it's doing. Why not? What's going on? And figure it out from there. So don't be blindly plotting things and saying, well, this is what I got. It must be right. Think about what it actually means to have a base that's less than 1 or a base that's greater than 1. All right, very good. Thanks, Beth. Let's let's talk now about, oh, did anyone have questions before we go to the next page? Okay. Wonderful. Let's talk about matching up a graph with a function. The graph of an exponential function is given. Select the function for the graph from the functions listed. Now, my suggestion to you here for this whole like figure out which function is which thing, you have some sort of an idea now what to expect in your graph. I would get an idea for which one you think it is, and then maybe put a table of values together to verify that those points are actually on your graph. So, all right, so you have an idea, and you know what? I'm going to even leave this out so that we can refer back to it, because remember that I was saying that even if your base is 3 instead of 2, your graph is going to have really similar properties. So notice that all of the functions that you're seeing here involve 3 to the x. Well, our function that we graphed here for number 2 is 2 to the x. 3 to the x is going to be similar. The only difference is it's going to increase more rapidly. That's the only thing that you're going to see. So that kind of gives you an idea of where to start. You know what the base function looks like. Now think about the transformations that are occurring. This one looks kind of similar to that, but notice it definitely doesn't go through the point 0, 1. So it's got to be shifted to the right. So I would not, and I know sometimes it's kind of hard to tell between A and B what the difference is. For A, you're taking 3 to the x and then subtracting 2 off of that value. For B, the -2 is occurring inside the exponent. So you can see it, but it's not the most obvious thing. I would definitely say it can't be C, because if it was C, then the graph would be going through the point 0, 1, which it's not. If x was 0, f of x would be 3 to the 0, which is 1. So that's a no-go right there. I definitely would say it can't be shifted down 2 units, because we said that this function had a horizontal asymptote at y equals 0. This one appears to have that same situation, so it can't possibly be shifted down 2 units. Otherwise, the horizontal asymptote would also be shifted down 2 units. I don't think it can be that one. Similar to this, gosh, now I can't even tell. You know, sometimes when I convert these in the PDF reader, when they start out in Word, like the font changes and everything gets funny looking. This to me looks like a +2 on the end. Now I don't even remember what it originally was. I think that this says this, which it still can't be, because that would mean that your horizontal asymptote would have shifted up 2 units. Not happening. So what you're going for is this one. I'm going to rewrite it just to make sure it's clear what this function is. 3 to the, and the exponent x -2. Now remember that when you subtract a constant inside the exponent, or inside the function in this case, that you're actually shifting to the right, not down. So this is your graph of 3 to the x shifted right 2 units, because you're seeing that happening inside that function. Now, you can verify just by setting up a table of values and making sure that you do indeed get the points that are on this graph. So you don't need a whole lot. But let's just look at a couple values and make sure that they're there. It might not be that helpful in this case to start at x equals -2, because, I mean, I don't know. That number would be so super small that it's really hard to see. If you wanted to, I would maybe start at x equals 0 and find f of 0. In that case, you're looking at 3 to the 0 -2, which is 3 to the -2, which is 1/3 squared, which is 1/9. Now, it's hard to tell if that's exactly 1/9, but it looks like it very well could be. So we're going to go ahead and try a couple more just to make sure. If you would like to skip over to 2, maybe you feel like the difference between 0 and 1 here is pretty minuscule, so maybe you want to check 2. Maybe do that. F of 2. The nice thing about f of 2 is that 2 minus 2 is 0, and 3 to the 0 is 1. So look at your graph and see, does it have the point 2, 1 on it? And indeed, it does appear that the point 2, 1 is on your graph. If you're still not satisfied, try one more. Maybe I would look at, you could try 4. F of 4 is 3 to the 4 minus 2, which is 3 squared, which is 9. And there is a grid on here. It might be kind of hard to see on my screen, but you should, depending on your printer. Well, actually, I technically had these printed and sent to you, unless you missed it for whatever reason. We do indeed, was that 10? Sorry, I thought the top point was 10. Have this point at 4, 9. So we can conclude that b is our function. On your homework, you're going to be doing some examples like this where you're just kind of trying to really match up the function, because in a lot of cases, these graphs are going to be multiple choice. And like I said, the difference between 2 to the x and 3 to the x is just one of them's rising more rapidly. But it's up to you to kind of figure out what else is happening to the function with the transformation. Let's do number 5 together also. Does anyone have a question about number 4? Okay. So number 5, notice the base here is 2. And it can't be 2 to the x because we already graphed 2 to the x and it did not look like this. So that one's out the window. So now your job is to figure out, well, if it's not 2 to the x, which one is it? Well, maybe think about what these transformations do to your graph. This is kind of a blast from the past. I know it was like a month ago, but it seems like forever ago. I'm trying to pick out maybe like the least complicated of all these, which maybe is either B or D. Let's look at D first. When you have a negative inside the function, not in front, but inside, is it a reflection about the x-axis or the y-axis? Some of you are probably just graphing this on your calculators and seeing, does this match? Yes or no? Negative in the function itself. X-axis reflection or y-axis reflection? I wish I had my 2-5 notes out. We would discuss. Okay, if you don't remember, I'll remind you. This is a y-axis reflection. And if you don't believe me, put it into your calculator. See if we can get it to graph today. 2 to the negative x. You already know what 2 to the x looks like. Now find 2 to the negative x. And there it is. 2 to the negative x is just your original function 2 to the x. Oh, losing it again. But reflected over the y-axis. So originally you had it going up from left to right. 2 to the negative x goes down from left to right. So that cannot be our function because we don't have that behavior occurring in our graph. So let's figure out which one it is. Focus. There we go. So this won't work. Negative 2 to the x. This is when you take your function and reflect it about the x-axis. I guess technically you could put this one in your calculator just to kind of verify, does this look right? instead of plotting points. We could do it that way. You do have your calculators at your disposal. Negative 2 to the x. That is your function. It's an x-axis reflection. So you took the original graph 2 to the x and you flopped it over the x-axis, and now it's heading down as you move from left to right underneath the x-axis. That's the winner. And if you were wondering, well, why didn't we talk about A? That one looks really exciting. It does have the 2 reflections to it. So you're going to see it being reflected about the y-axis and then over the x-axis. So that would look like negative x. This, which is not your function. But now you have a really good idea of how to generate these functions. And totally, you're being reminded of all of the awesome stuff that you learned in 2.5. Okay, so this one is B. Now, you guys do number 6 while I focus on attendance, which I lost, but it's very close. Your base is 5. Wonderful. All right. Gosh, that takes a long time. All right, what did we come up with? A, B, C, or D? Oh, I see some A's. Yes. Oh, yes. Awesome. A's. Wonderful. I agree. And it kind of helps that we went through these reflections over the last example. Yes, it is A. I absolutely agree. Remember we talked about A being, or not A, I should say. We have a y-axis reflection when you have the negative sign inside the function, which is happening in this case. Now, you could always graph it just to make sure, but you can also use the process of elimination. This example would be a reflection over the x-axis. Now, because it's 5 to the x, 5 is greater than 1, you're expecting that your function normally should be going up and to the right. But if it's reflected over the x-axis, it's going to look more like that. That's not what's occurring here. And then 5 to the x, again, we're expecting this behavior where the graph goes like this. Not happening here. And then this one would be both reflections. So reflecting about the y-axis, reflecting about the x-axis, like that. So you do indeed have A occurring. Very good. You guys feel like you have a pretty good handle on those transformations? All right. Wonderful. All right, so to summarize, characteristics of exponential functions of the form f of x equals b to the x. Now, the domain consists of all real numbers. There's no value for x that you cannot allow in the exponent. So, I mean, assuming that, well, your exponent wouldn't have like any variable in the denominator for b to the x, but you can plug in any value you want for x and you will still get a value for y. So you have a situation here where your domain is all real numbers. Your graph is going to always be smooth and continuous. You can draw the whole thing without picking up your pencil. The range of f of x equals b to the x consists of all positive real numbers. Now, notice that the range starts at 0, but does not include 0. So any value of y that's greater than 0 up to infinity, and this is for your base function b to the x. The graphs of all exponential functions of the form f of x equals b to the x pass through the point 0, 1. That's why I kept calling it that anchor point. It's on all of the graphs, and then if they get shifted, that point's going to move. Otherwise, that point is there regardless, because f of 0 equals b to the 0. The y-intercept is 1. There's no x-intercept. There cannot be because you have a horizontal asymptote on the x-axis. And then we discussed that if b is greater than 1, the graph goes up and to the right. If b is between 0 and 1, I guess we actually said less than 1. We should be a little bit more specific here. B technically can't just be less than 1 because b has to be positive. But a value of b that's between 0 and 1 is going to have a graph that goes down to the right. F of x equals b to the x is 1 to 1 and has an inverse that is a function. I don't know if you guys remember what it means to be a 1-to-1 function. That just means that you pass the vertical and the horizontal line test. And let's see, it has an inverse that's a function, and we'll talk about that when we start talking about log functions. And the graph approaches but does not touch the x-axis. The x-axis is a horizontal asymptote. So that's kind of just a summary of everything that we've talked about so far with graphing these exponential functions. Now, let's switch this up a little bit and talk about functions with a base of e. Now, e is this transcendental number. You can always get it in your calculator. It's on here as the second to the natural log button. So if you hit second natural log, that's going to pull up e for you. And then you're going to get an exponent. Mine, of course, shows up as an exponent. Yours might have the caret. But you just put into the first power, and e will be the base. The base to the first power is e to the first. And that's where you get this number from. E equals 2.718281827, and it keeps going and going and going and going. It's a transcendental number. It occurs a lot in nature. It's used in a lot of applications. It's a very important number. So you don't have to memorize this whole number. It's helpful to at least know that it's about 2.72 to give you a good idea. The irrational number e, approximately 2.72, is called the natural base. The function f of x equals e to the x is called the natural exponential function. So let's use the graph of e to the x to obtain the graph of g of x equals 2e to the x. Now, in order to do that, you need the graph of e to the x. Now, in order to graph e to the x, you don't have to get crazy with a bunch of values. And I know there are a lot of decimals here, so it can get a little tricky. Basically, you just need really like 2 points to get a good idea of what this graph is doing. You know that any real number to the 0 power is 1. So this function is still going to have the point 0, 1. Maybe I'll put this in another color so we can differentiate. And then if x equals 1, we just have e to the first power, which is about 2.72. You can't get that specific on your graph anyway. So do the best you can. If x is 1, then y is about 2 3/4, right there. Now, you know the behavior of this graph. If you want to put one more point on it and look at what happens at 2, that's fine. Take e squared. And you'll get about 7.4-ish. Sorry, it gets harder and harder to see this thing as the evening wears on. 7.4-ish. So we can pop that point on here. Right there. I wouldn't even worry about the other points because you know that this really just follows the rules for f of x equals b to the x. E is a real number. It's greater than 1. You know that these values are going to increase as x gets larger. And then you know that the function values are going to approach this horizontal asymptote at y equals 0 as x gets smaller. So to graph e to the x, you can just connect these with a nice smooth curve. So this would be f of x. So very similar to f of x equals 2 to the x, because it's not 2, it's 2.72. A little bit closer to f of x equals 3 to the x. Now, what we're going to do is we're going to take these points on the graph and graph g of x equals 2 e to the x. Now, if you already have the e to the x function on there, you don't need to actually plug in a bunch of values into your table. Remember that this is just going to be a vertical stretch. So we're going to say we're going to vertically stretch f of x by 2. And if we're vertically stretching f of x by 2, it just means that we're going to multiply the y values by 2. So multiply the y coordinates of f of x by 2. Now, if all I asked you to do is graph g of x equals 2e to the x, you might want to plot some values. But if you already have f of x on here, you can just go ahead and leave the x values the same, but just multiply the y values by 2. So you probably already still have these in your calculator. You have e to the first power. Actually, we'll do these in reverse. If you already have e to the second, now you'll get 2e to the second. Well, there it is, which is about 14.8. Our graph doesn't go that high, but that's okay. We're going to get some good behavior of the graph based off of what's happening maybe at e to the first power. So we'll just take 2e to the first, and we'll get approximately 5.4-ish. So we can take this point at 1. And then instead of saying 1e, we have 1, 2e, which is 1 and then about 5.5-ish right there. So that point's going to be on G. The other point that we had that was important was the point at 0, 1. Leave the x coordinate the same, multiply the y coordinate by 2. So if you already have the point at 0, 1, well, your new graph g of x is going to have a point at 0, 2. And then you know that this graph is going to be behaving the same way as x gets smaller. So you already have the graph on here. Just go ahead and sort of model this behavior. It's going to get larger more quickly. If you would like to get a value for -1, that's fine. You can pop into your calculator something like g of -1. And then you can do like 2e to the -1st, just to verify how small that's getting, which we will do here. And you get like 0.74-ish, which is about right here. And then from there, you know you're just approaching the x-axis. So this purple line will be g of x, or this purple curve, I should say. And that's how you use F to graph G. Just look at the transformation that's occurring and figure out what you need to do to the coordinates to get from one graph to the next. You can see this stretch also, how your original function F is sort of being stretched out vertically by this factor of 2. Does anyone have a question on number 7? Okay. Solve the problem. The population in a particular country is growing at the rate of 2.8% per year. If 7,638,000 people lived there in 1999, how many will live there in the year 2005? Use f of t equals y sub 0 e to the 0.028t and round to the nearest 10,000. Okay, so we have a couple of things to do here, a couple of important things. You were given this function. It's a growth function. You were told that the population in a country is growing. You were also given the rate at which the population was growing. It is important for me to note to you that the rate at which the population is growing is included in this exponential function. And like I said, you're going to be writing these on your own in 4.5, and we're really going to dissect these and talk about what each part means. Right now, all you have to do is evaluate it. But when you are given this rate in the function, it's given to you not as a percent, but as a decimal. We never use percents in any sort of growth or decay functions. So it's given to you here as 0.028 to represent the 2.8%. All right, so you have 7,638,000 people currently living in this country, or I would say they were living there in 1999. How many will be there, which is funny, will be there in the year 2005? Can you tell how old this problem is? Very, very old. Very old. We're going to use this function to determine that value. Now, this value, f of t, is going to tell you the new population in 2005. Whenever you see this y sub 0, it really means like y sub naught. This is like the initial population. So what this function is doing is it's taking the initial population and it's multiplying it by this growth factor. Now that factor is going to depend on how long the growth is occurring. You were not given us a particular value in this problem for t. However, you were told that the initial population was from 1999, and the population that you're looking at is happening in 2005. So we're going to use t equals 6 years. Now, I was thinking maybe you were wondering, why are we using 6 years here where the first problem we did in this section, we used 12 months? Well, it's really important to note what was given to you initially as the growth rate. Let me go back to this first problem to remind you of what I'm talking about. Notice here that you were given the growth rate of 5% monthly. Normally, we don't do this in months. Normally, it's years, but you were given that in this problem, so that's what you go with. The 5% is right here in its decimal form, and you multiplied the monthly rate by the number of months. Similar thing is occurring here. This time, you were given a rate as 2.8% per year. That's why you want to use the time in years and not months. If you do use the time in months and you use 72, you're going to get this crazy huge population. So don't do that. We'll use t equals 6 years. And remember, because that is 2005 minus 1999 equals 6. And then everything else at this point is just plugging it into the function. So we're going to find f of 6, which is equal to the initial population, 7,638,000, times e to the point, and be careful with your zeros here. I don't care if you include the leading zero that's in front of the decimal. Just make sure that the zeros behind it are good. Okay, so 0.028, and then we'll multiply that by our value of t, which is 6. And we're just going to put this into our calculators. I've already shown you where to find that E button on your calculator. Other than that, just be careful making sure that you input all of this correctly. So we're going to have 7,638,000, so include those 3 zeros, times, we're going to, pulled up the wrong function, E, times e to the 0.028 times 6. And that times 6 has to be inside your exponent. Eventually, I'm going to get an emulator, and it's going to be like the week before the final exam. You just watch. And you are going to get approximately 9,035,270. Round to the nearest 10,000. Okay. So let's go ahead and put our answer down, and then we'll round it off. So you had 9,035,269.832. You should also be asking yourself, does this answer make sense? You originally had 7 million. The population after 6 years is growing by 2 million. I mean, that's a lot, but it's reasonable. It's not like you went from 7 million to like 35 million. So let's go ahead and write this as 9,035,000. Oh, we were supposed to round it to the nearest 10,000. So be careful with your rounding. If we're rounding to the nearest 10,000, we're going to your place values here. Ones, tens, hundreds, thousands, 10,000s. So to the nearest 10,000 means you go to the right of the 10,000s. If that number is 4 or less, you keep this digit the same. If the number to the right is 5 or greater, then the digit in your 10,000s place goes up. So this will actually go up from a 3 to a 4. So that would be your population to the nearest 10,000. Does anyone have a question on number 8? And if you're labeling it, which is always a good thing to do, people. All right, the other really important thing that we're going to do today using exponential functions is we're going to talk about compound interest formulas. I actually find these to be kind of fun and satisfying. And they always make me think of my student loans, which we're still paying off. It's a very sore subject, especially since I only teach one class. Either way, yeah, don't get a lot of student loans. It's a really bad idea. I didn't even get that many. That's the crazy thing. I don't have that much. It's just the interest. The interest is insane. I got to refinance. All right, let's see. After 2 years, balance A in an account with principal P and annual interest R in decimal form, that's very important, is given by the following formulas. Now, you're going to be specifically told in the problem what type of compounding is happening. So you're not going to have to worry about which formula should you use. If you're given the number of times or the number of n compounding periods per year of this loan or whatever it is that you are discussing, some sort of bank balance, a lot of times is the case, then you're going to use this formula. A equals P times 1 plus, sorry, my plus looks like a minus, R over N to the NT. I'm even going to rewrite this because it didn't come out right. So the NT is in the exponent. That's if you're given the number of compounding periods. You might be told that the compounding is continuous. In that case, you have a formula for continuous compounding. It's A equals P times E to the RT. Some people call this PERT. Call it PERT if you want to. I'll know what you're talking about. But technically, the RT is in the exponent. So we're going to use these to find accumulated values that are either in an account or on a loan balance after a certain number of years. Now, interest is normally a little bit more complicated than this, but these formulas are used and they are important formulas. So first we're going to use the compound interest formula to solve, because we are given periods for these values compounding. Number 9, find the accumulated value of an investment of $3,000 at 8% compounded annually for 9 years. So the most important thing is to properly identify what information you're being given. In this section, most of the time you're looking for A because you don't know how to solve these exponential equations yet in order to solve for a value that's in the exponent. So we're going to find the accumulated value. That means find A of an investment of $3,000. Now, you were told here that P is the principal. That means it's the initial amount, whether it was an initial investment or an initial loan value. The principal is the initial amount in the account. So find the accumulated value of an investment of $3,000. So the $3,000 is the principal. That's going to be P. At 8%, now the percent is R, but remember, we don't actually write the rate as a percent. We write it as a decimal. So don't write R equals 8. No, write it as R equals 0.08. Remember that when you want to switch a percent to a decimal, you need to move the decimal place to the left 2 times. So if you have 8%, 8 is officially like 8.0. Move that decimal place to the left twice, and you get the rate in decimal form. Or divide by 100, do it that way. This is compounded annually. Now, remember that N is compounding periods per year. So N has to do with how many times that interest is compounded. If it's compounded annually, that means it only happens once per year. So compounded annually is not very common for what we're going to be doing, but it can happen. So we'll say that that means n equals 1. And then we're talking about looking at the value of this investment after 9 years. So t will be 9. And that's all we need. In order to find the accumulated value, we need P, R, N, and T. And we have all of those components now. So we are going to make sure we put them correctly into the formula and that we enter these properly in our calculator, because that's the worst part, when you have the actual equation just right and then your number's wrong because you entered it wrong. Now, remember, this is the formula that we're using because we were given the number of times this compounds per year. Otherwise, we would have been told the compounding is continuous, and we weren't told that. So we're using this formula. So A equals P, which is the principal, so 3,000 times, in parentheses, 1 plus R is 0.08 over N to the N T. And, you know, if N is 1, you don't have to write it. I'm just writing it because I'm the teacher. Does anyone have a question so far? You know, I missed something else on my chat. Oh, we were talking about student loans. Yeah. Yeah. I know. I'm not 40 yet, but hopefully they'll be paid off by then. Who knows? Who knows? I remember being a student at ECC, and Amy Beth Maurer was telling me that she was still paying off her student loans. And at the time, I thought she was old, but she wasn't old at the time. But I was like, really? Wow. I was totally shocked by that. I didn't know that was a thing, but yeah. I mean, I know people who pay like $1,000 a month on their student loans, and they still are going to be paying them off for a long time. It could be a lot worse. Okay. Yeah, loans are, whew. Yeah. Doctors, chiropractors. I know people who are dentists who owe like $500,000. Yeah, not a good thing. Okay. The cost of education, you guys know better than anyone else. When I went to ECC, it was a lot cheaper than it is now. All right, let's go ahead and evaluate this. Oh gosh, I put in T. I should have put in 9. Look at me, I'm just yapping away about my loans because it's such a sore subject. Okay, put this in my calculator. Okay. 3,000 times, in parentheses, 1 plus 0.08. You don't have to divide by 1 in this case, to the 9th power. This is what it should look like. If you have an older calculator and you have the caret symbol, that's fine. Make sure that you have closed off your parentheses and then you have it to the 9th power. The parentheses are very important here. And you end up with $5,997.01. And this is money. So when you're talking about money, you don't want to, round to like 3 decimal places. That wouldn't make any sense. Normally you'll round to the nearest cent unless you're told otherwise. And then you'll ask yourself, does this make sense? There was an initial investment, and an investment means you're putting in money and you're hoping to get more back out of it. And then it was growing. And it was growing for 9 years. So definitely if you got something like 205, you'd be like, this can't be right, because that meant I lost a lot of money, which, yeah, technically it could happen depending on how it was invested. But this problem is specifically stating that it's growing at 8% for 9 years. So yeah, you're expecting a value more than $3,000. So that's a pretty good return. Any questions on number 9? Okay, now you guys do number 10. Now, if it's compounded quarterly, how many times per year does it compound? 4, yes, agreed. Compounding quarterly means n equals 4. So we should have 1,500 times 1 plus 0.10 divided by 4 to the 4 times 2. Mm-hmm. 1,500 times 1 plus 0.10 divided by 4 to the 8th. 1827.60. Does anyone have a question about how to arrive at that answer? Okay. Wonderful. All right. So now we'll use the other formula and we'll talk about what happens to have interest that compounds continuously. And if you are not sure what it means to compound, it basically just means it's the value that's being added to your balance or how often that value is being included in the balance. Find the accumulated value of an investment of $3,000. So there's your P at 7%, compounded continuously for 6 years. Now, the compounding continuously formula is even easier to use because it's just A equals P e to the RT. So our P, I almost wrote P, but it doesn't make sense to do that, is 3,000. And then we have E to the 0.07 times 6. And really, this is just a matter of, can we identify the pieces of the function and can you put it into your calculator correctly? I have no idea why this thing is not beeping at me whenever there's something in the chat. It used to beep at me. Okay. So when you put this in your calculator, very similar to what we did before, 3,000 times E to the 0.07 times 6. Make sure that that 6 is also in your exponent. And you should get 45, 65, 88. Now, if you're wondering, okay, what does all of this mean for some practical application? In the next example, we're going to compare which investment yields the greater return. Before we do that, does anybody have a question on number 11? Okay. All right, suppose you have 10,000 to invest. So there's your principal. Which investment yields the greater return over 6 years? Is it 8.75% compounded continuously or 8.9% compounded semi-annually? So let's do the continuous first because that one's a little bit easier to work with. So your principal is 10,000. Your rate, when it's compounded continuously, be careful not to grab the wrong rate, is 8.75%, so 0.0875. And you do need all of those decimal places in there. And then T is 6 years. Now, if you want, you can just set up both equations and then put them both in your calculator at the same time. That's what I will do. And then we'll compare that to what happens when we take that same principle and we invest it such that we are compounding semi-annually at 8.9%. So the percentage is higher. However, you're not compounding as often. So 1 plus R 0.089 over N. Semi-annually, it's not necessarily always clear. Semi-annually means twice a year. So if you're very into the sales and you know about the semi-annual sales, you know it happens twice a year. So semi-annual means 2 times. And then we have 2 times 6. And then you'll put these in your calculator and see which one yields the greater return. So the first one is 10,000, don't forget all your zeros, times e to the 0.0875, don't forget all your zeros there, times 6. And you are expecting here $16,904.59. Which makes sense. 6 years at 8.75%. It's gonna yield a pretty good return. For the next one, we're gonna take our 10,000. We're gonna multiply that by, in parentheses, 1 plus 0.089 divided by 2 to the 12th power. You'll get 16,861.70. So what's interesting about this is even though your rate was greater when you compounded semi-annually, you were at 8.9%, does not matter. The continuous compounding actually yielded the better return at the lower rate. So this is a pretty common problem. You will see one of these on your homework where you need to compare and determine which one yields the better rate. In this case, it is the continuously compounding investment. Does anyone have a question on number 12? Okay, that was 4.1. Let's talk about logarithms. We're going to spend much of the rest of our time in this chapter discussing logs and kind of moving back and forth between logs and exponential functions. Let's see, 4.2 is, yeah, so we're going to spend a lot of time working around with these logs in 4.3. I'll introduce you to the logs in 4.2. First and foremost, a logarithm is an exponent. In case you need me to, I'll be reminding you all the time, but we'll write it down. A logarithm is an exponent. So something bizarre happened to me that will always affect the way I teach college algebra. When I was in college algebra as a student, my teacher, it was a summer class and like we didn't have a lot of time. And instead of being like, okay, we can skip this section because you're not going to need that, and we can skip that section, he was like, let's just skip chapter 4. We can either skip chapter 4 or skip chapter 7, and we'll just skip chapter 4. And of course, we were like, cool, don't have to do exponents and logs. I had actually never seen logs, and then I got into Calc 2, And I really got stuck because all of a sudden we were differentiating and integrating logarithmic and exponential expressions, and I hadn't really had to use them. And that's, I guess, the unfortunate thing is you make it all the way from college algebra until Calc 2 before you actually really end up using them again. But I had to totally learn how to do exponents and logs on my own. And my teacher was like, well, I mean, it's so basic. It's just, my Calc 2 teacher this is. He goes, a logarithm is an exponent. So whatever. I was like, okay. But it really did kind of help me work through it. And I'll kind of be reminding you along the way that a logarithm is an exponent, because I found it to be actually helpful as I worked my way through teaching myself logs. And I didn't know any of their properties or any of the ways you could rewrite them. It was terrible. That is why when I teach college algebra, I try to be very strategic about anything that I skip. I try to make sure that it's nothing that you're gonna have to be responsible for later. Like 3.6, when are you gonna use that again? Like, I don't know, I never use that. 3.7, you saw it in Math 98, you probably won't ever see it again. So chapter 4, extremely vital, cannot be skipped. Definition of a logarithm function. For a positive value of x and a positive value of b, such that b cannot be equal to 1, y equals log base b of x is equivalent to b to the y equals x. Now, I'm going to write this in English because I want you to know how to say it. Y equals log base b of x. So y equals log base b of x is equivalent to b to the y equals x. Now you can kind of see where this whole logarithm is an exponent thing comes in. In this case, sorry, I swear, when this gets converted, funny things happen to the font. It's b to the y equals x. Notice that the y is in the exponent. Well, remember that the equal sign means is. This logarithm is the exponent. The exponent is y. The base is b. The base is b. And then x is just the argument of your log. That'll be on the other side of your equal sign. You're going to need to work back and forth between this definition and that one. We're going to be going back and forth between these throughout the chapter. So it's really important that we can convert from one to the next. And we're going to spend some time converting just to make sure that it makes sense, but you're going to be using it a lot. The function f of x equals log base b of x is the logarithmic function with base b. So now we're going to take an equation and write it in its equivalent exponential form. And you're going to see several of these on your homework, just asking you to convert back and forth. So what you're going to do to write this log expression in exponential form is you're going to take the base of the logarithm and you're going to make it the base of your exponential expression. And then if you remember that a logarithm is an exponent, then you'll remember that the 2 is in the exponent. And then equals the argument of your logarithm. Now this one makes sense because this one actually has numbers in it, and you know that 3 squared equals 9, so no big deal. We know this is true. That won't always be the case. Sometimes you'll have variables. A lot of times you'll have variables, and you won't know which part's going where just by eyeballing it. So make sure that you take the base to the exponent to get that log argument. And you end up with 3 squared equals 9. Does anyone have a question so far? Write the equation in its equivalent logarithmic form. So now we're going to work back the other direction. We're going to take our exponential form and turn it into log form. In order to do that, I'm going to first write my log. The base of the log comes from the base of the exponential expression, which is 5. We're taking 5 to the second power. So the base for our log is 5. And then the argument for our log is on the other side of the equal sign. A logarithm is an exponent, and the exponent is 2. I also think you're going to get used to looking at these and just visually saying, okay, 5 squared is 25, and just kind of moving kind of from the left to the right to the middle. 5 squared is 25. Everyone's going to see these a little bit differently. Questions on number 2? Number 3, we have the cube root of 125 equals 5. This one doesn't appear that it has an exponent. It has a radical. You're going to have to rewrite this in order to write it in log notation. So instead of writing the cube root of 125, you're going to rewrite this as 125 to the 1/3 power. Now, if it's been a while since you've rewritten your radicals with rational exponents, you need to refamiliarize yourself. A cube root is a 1/3 power. A square root is a 1/2 power. So on and so forth. So this is not the objective. We just need to rewrite it in order to actually write this in log form. So to write it in log form, I'm going to write my log. Base would be the base of your exponential expression. So log base 125 of 5 equals the exponent, which is 1/3. 125 to the 1/3 equals 5. I really enjoy talking about logs. They're very subtle, very succinct. There's not like a whole lot of hoopla that goes with them. You just kind of have to know the rules. And I'm going to show you some rules right now. Properties, I should say. Properties of common logarithms. All right, log base b of 1 is 0. Now, it's helpful if you memorize these just because your work will go more quickly. But remember that you can always generate these on your own because you know that b to the 0 equals 1. So whenever you have a 1 in the argument of your log, doesn't matter what the base is, your exponent has to be 0. Similarly, b, the base, to the exponent of 1, b to the first, equals b. So that's another common property. So whenever your base matches the log argument, your log is going to be equal to 1. The reason we're going over these is because we're going to be doing a lot of like simplifying and evaluating log expressions. So we need to know how to do that. Something similar occurs here. The difference between 2 and 3 is that in number 3, you have an exponent on the argument b. As long as the base and the base of this log argument match, then the x just comes out on its own. And then you have something similar. You won't see it a lot, but you will see it for these types of problems. B to the log base b of x equals x. And you will have your notes on your exam. So some of these you'll memorize just because you'll do them so often. These ones are probably the most important, but this will probably stick with you also. And then these are general properties. A common log is a base 10 log. You have the same properties. This time, when it's log base 10, the base is not written. So log of x really means log base 10 of x. It's assumed. It's kind of like when you write x, it's assumed to be 1x. So if you just see a log and you don't see a base on it, it's assumed to be a log base 10. So that's very important. All of these have a base of 10 on them. If it's a common log, it's a base 10 log. All right, so log of 1 is 0, log of 10 is 1. That's because 10 to the first equals 10. If you don't like this and you want to write a base on it, sometimes I write bases on them anyway because I just find them easier to work with. That's fine. Put a base on it, but you might not have it displayed with one. 10 to the x equals 10 to the x. And then here, your exponent matches, or I'm sorry, your bases match, so you just get x. These are properties. Like I said, memorize them if you want. The most important ones are 1, 2, and 3. 1 and 2 are most important, but you'll have your notes. So if I were you, I would highlight this or maybe put a big box around it because these properties are very important. Highlight. But we're going to use them right now. I just want them to be easily found in your notes when you're working on your homework and on your exam. Okay, number 4, evaluate the expression without using a calculator. All right, so the logarithm is the exponent. We're trying to find out what the logarithm is. So you're asking yourself 4 to what power is 64? Now, if you want to think about it that way, you may do it that way. If you want to think about it using the log properties we just talked about, do it that way. If anything, I think, I don't know, depends on the problem. I'm going to show you how to use the properties because I like them. We can rewrite this because 4 and 64 share a common base. I can rewrite 64 as 4 to the 3rd power. Now, if you're not familiar with thinking about 4 cubed as being 64, then you might have an easier time. Well, I guess you would need to know that anyway, regardless of whether you're using the property or not. If you're being asked to evaluate the log expression, most of the time, if it says without using a calculator, it wants you to use these rules. That means you can use them. So try to rewrite these so that you can use the rules, which in most cases means you're going to try to work around with the base. So 64, I can rewrite with a common base. And then I can go up here and think about, which one of these properties does this match? Well, I have log base b of b to the x matches number 3. So you can go ahead and say that it must be the case that as long as my 2 bases match, I can just keep the exponent. And conversely, if you're asking yourself 4 to what power is 64, well, that power is 3. So if you want to do that, I'll write that in English. 4 to what power is 64? That's really what you're asking yourself when you're evaluating these log expressions. All right, so this would be using the properties. That would be kind of thinking it through. Does anyone have a question on number 4? Okay. So let's do a couple more. Number 5, log base 12 of the square root of 12. Now, most of the time when you're evaluating these log expressions, you don't want radicals in your expression. You're going to rewrite these with rational exponents. So let's rewrite this as log base 12 of 12 to the 1/2 power. A square root is a 1/2 power. And now you're in another situation where the bases match. Therefore, your answer would be the exponent 1/2. So 12 to the 1/2 power equals 12 to the 1/2 power. Sometimes it sounds like circular reasoning. Log base 4 of 1. This gets you to general property number 1. Log base b of 1 is 0. That's because 4 to the 0 power equals 1. Number 7, also using these general properties for logarithms, you have log base b of b. That gets you to rule number 2. Log base b of b is 1. That means log base 11 of 11 is 1. Because 11 to the first power equals 11. Does anyone have a question so far? Now this one, you're not going to see a lot, but for some reason it kind of stands out. I feel like it stands out a lot. This is b to the log base b of x. This is number 4. Your answer is just x11. The bases match. Take the 11 out. Take the exponent out. Same idea with number 9. Number 9 actually follows number 3. Maybe I should be writing down which ones these are. This one follows number 3, which is log base b of b to the x equals x. This was number 2. That was number 1. Okay, we're going to talk about graphing log functions next time. We're going to be using exponential functions to graph our log functions. I'm going to put up some homework for you all available at 7:50 that'll cover 4.1 and part of 4.2 up to graphing. So you have all kinds of things to keep you busy this weekend. If you have questions, I will be on for another 15 minutes, so feel free to stick around. Otherwise, have a good weekend.